Pick up a handful of sand. That's your starting point. Not a factory, not a blueprint, not a government contract. Just a fistful of crushed rock sitting in your palm. Now build a rocket. Not a firework, not a model. A real, orbital launch vehicle capable of reaching space and surviving the journey. That challenge sounds absurd until you realize that every rocket ever launched was ultimately made from something that started exactly like that raw material pulled from the ground. A rocket is not a single invention. It is the final invention. The one that only becomes possible after civilization has already solved dozens of other impossible problems first. So what's the first thing humanity would need to reinvent before even thinking about space? Start with the sand itself. Silicon dioxide. The primary compound in most beach and desert sand is one of the most abundant materials on the surface of the Earth. But a rocket isn't built from sand directly. Sand is the beginning of a much longer story, because locked inside ordinary rock and ore, there are metals. And metals are everything. The structural frame of a rocket, its fuel tanks, its engine bell, its combustion chamber, all of it requires metal refined to extraordinary standards. Iron comes first. Humans figured out iron smelting roughly 3,000 years ago, and it changed civilization more than almost any other discovery before or since. You dig ore from the ground, you heat it in a furnace hot enough to separate the metal from the rock, and you get crude iron. But crude iron is brittle. It cracks under stress, and a rocket airframe that cracks on the launch pad is not a rocket. It's a very expensive explosion. Steel is what you actually need. Steel is iron with a carefully controlled fraction of carbon mixed in, typically somewhere between 0.2% and 2.1% by weight. And that small addition transforms a brittle metal into something with tensile strength that iron could never match. The Bessemer process, patented in 1856, was the first method that allowed steel to be produced cheaply and at scale. But even steel isn't enough for the most punishing parts of a rocket. A rocket engine's combustion chamber burns propellant at temperatures that can exceed 3,000 degrees Celsius. That is hotter than lava. That is, in fact, hot enough to melt most grades of steel. The solution is a family of materials called superalloys, nickel and cobalt-based alloys developed during the 1940s and 1950s, specifically because engineers building jet engines kept melting their turbines. NASA's Saturn V engines used a nickel superalloy called Inconel in their combustion chambers, a material capable of maintaining its structural integrity at temperatures that would reduce ordinary steel to liquid. So before you build a rocket, you have to build a metallurgical civilization. Mining, smelting, alloying, heat treatment, quality control. An entire industrial chain has to exist and function at scale before a single rocket component can be fabricated. Now assume you have the metal. The next question the Trello brief raises is exactly right. How do you shape it with enough precision to survive launch? The answer is machine tools. And this is where the story gets recursive in a way that should stop you cold. You cannot build a rocket engine by hand. The tolerances involved, gaps measured in hundredths of a millimeter, surfaces polished to near optical smoothness, threads cut with sub-millimeter precision, require machines. The lathe is the foundational machine tool of the industrial age, invented in its modern form in 1797 by Henry Maudslay in England. The metal cutting lathe allows a craftsman to rotate a piece of metal against a hardened cutting tool and carve it into a perfectly cylindrical shape with a precision that no human hand can replicate unaided. From the lathe came the milling machine, the drill press, the grinding wheel, the boring mill, an entire ecosystem of precision machinery that built the Industrial Revolution. But here is the part that most people never think about. You need machines to build the machines that build the rocket. The lathe that cuts the combustion chamber was itself built on another lathe. That lathe was built on another one still. Follow the chain backward and you eventually arrive at human hands. But you also arrive at centuries of accumulated engineering knowledge embedded in steel and cast iron. A civilization starting from zero would spend generations just developing the machine tool industry before it could think about aerospace manufacturing. Now you have precise metal parts. The next problem, the one that actually makes a rocket, is propulsion. What makes a rocket move? The answer is one of the oldest principles in physics, articulated by Isaac Newton in 1687. Every action has an equal and opposite reaction. Burn propellant. Expel the exhaust at high velocity through a nozzle, and the vehicle accelerates in the opposite direction. But the chemistry behind that burning took centuries to understand and refine. The first rockets were Chinese military weapons from roughly the 10th century, burning a mixture of potassium nitrate, charcoal, and sulfur, the compound we call gunpowder, packed into bamboo tubes. The key insight embedded in gunpowder is that the potassium nitrate acts as an oxidizer. It supplies the oxygen needed for combustion from within the mixture itself. That means a rocket doesn't need air to burn. That is the entire secret of spaceflight in one chemical principle. Modern liquid-fueled rockets take this concept to a far more powerful extreme. Robert Goddard launched the world's first liquid-fueled rocket in March of 1926, burning liquid gasoline and liquid oxygen, and demonstrated that controlled, throttleable rocket propulsion was physically possible. The German V-2 rocket of the 1940s, which became the technical ancestor of every modern orbital launch vehicle, burned ethanol and liquid oxygen, generating about 25,000 kilograms of thrust. Liquid hydrogen and liquid oxygen, the combination used in the Saturn V upper stage, releases more energy per kilogram of propellant than almost any other chemical reaction available to engineers. But liquid oxygen boils at negative 183 degrees Celsius. Liquid hydrogen boils at negative 253 degrees Celsius, just 20 degrees above absolute zero. Handling, storing, and pumping these propellants requires cryogenic engineering of extraordinary sophistication, including insulated tanks, high-speed turbopumps spinning at tens of thousands of RPM, and precision valves that must open and close reliably in environments that would destroy ordinary mechanical components instantly. The chemistry and the engineering are inseparable. You cannot have one without spending decades mastering the other. Now assume the rocket burns. A vehicle generating 3 million kilograms of thrust is also carrying around 2 million kilograms of propellant, and the slightest misalignment of thrust will send it cartwheeling off course within seconds. How do you stop a controlled explosion from flying in the wrong direction? The answer required building an entirely separate technological civilization: electronics and computing. Gyroscopes, spinning masses that resist changes in orientation due to angular momentum, were first applied to vehicle stabilization in the early 20th century. Hermann Oberth and Wernher von Braun's team used gyroscopic guidance systems on the V2, feeding error signals to graphite jet vanes that could deflect the exhaust and steer the vehicle. But gyroscopes alone drift over time. Modern rockets use inertial measurement units, clusters of accelerometers and ring laser gyroscopes, that measure every change in velocity and rotation hundreds of times per second and feed that data into onboard computers. Those computers run guidance algorithms that adjust engine thrust vectoring in real time to keep the vehicle on course. The guidance computer for the Saturn V's instrument unit, a ring of electronics mounted just below the third stage, performed about 1 million calculations per second. It sounds modest by modern standards. In 1969, it was the most capable flight computer ever built. To build a guidance system, you first have to build the transistor. To build the transistor, you have to grow single crystal silicon with purity levels that weren't achievable until the mid-20th century. To grow that silicon, you have to understand quantum mechanics, solid-state physics, and semiconductor fabrication, fields of knowledge that took the entire accumulated scientific output of human civilization to develop. A rocket, it turns out, requires a computer. A computer requires a transistor. A transistor requires physics that took 2,000 years of accumulated thought to produce. Now suppose the rocket launches, clears the atmosphere, and the engines cut out. The common assumption is that reaching space is the hard part. It isn't. Getting 100 kilometers above the Earth's surface, the Kármán line, the conventional boundary of space, requires reaching a speed of roughly 1 kilometer per second vertically. A large firework can almost do that. Reaching orbit is something else entirely. Orbit isn't about altitude. Orbit is about horizontal speed. To stay in low Earth orbit without an engine, to fall around the planet in a continuous arc rather than falling straight down, a vehicle must be traveling at approximately 7.9 kilometers per second horizontally. That's roughly 28,000 kilometers per hour. At that speed, the rocket is not floating in space. It is falling continuously in a curve that matches the curve of the Earth beneath it. The Earth literally curves away as fast as the vehicle falls toward it. Achieving that horizontal velocity from a standing start requires shedding dead weight as propellant burns, which is why every serious orbital launch vehicle in history has used staging. The concept was formalized by the Russian physicist Konstantin Tsiolkovsky in his rocket equation of 1903. The more propellant a rocket must carry relative to its dry mass, the more velocity it can achieve, but the returns diminish quickly. Staging solves the problem by dropping empty tanks and engines once they're spent, so the remaining vehicle isn't hauling useless mass. The Saturn V discarded 3 stages on the way to the moon, each separation precisely timed and explosive bolt triggered to the millisecond. Every single stage required all the metallurgy, machining, chemistry, and computing that came before it. Multiply that by 3 and then add the spacecraft on top. Step back and look at what just happened. A rocket is not a machine. A rocket is an argument, a physical proof that metallurgy, chemistry, precision manufacturing, electronics, computing, and a dozen disciplines of pure science can be integrated into a single functioning system. Every field of human knowledge is embedded in that structure. The alloys in the engine carry 3,000 years of material science. The propellant chemistry carries 400 years of systematic experimentation. The guidance computer carries a century of physics, mathematics, and electrical engineering. The machined components carry 200 years of industrial tooling. None of it was built for the rocket. All of it was built for something else, and then the rocket claimed it. If humanity lost everything tomorrow, the factories, the textbooks, the institutions, the accumulated knowledge, and had to start again from a handful of sand, the answer isn't decades. It's centuries, possibly longer. Because you can't skip the steps. You can't reach orbit without computers, and you can't build computers without semiconductors, and you can't fabricate semiconductors without machine tools, and you can't build machine tools without steel, and you can't make steel without mastering fire first. The rocket is not the achievement. The rocket is the receipt, a printout of everything civilization had to learn before it was allowed to leave.